Okay. Okay, great. Can everyone hear me? Yes, you can. Welcome to the class. So this will be the first lecture, kind of a bit more serious. And what will we talk about today are two topics. First, I'll show you some ways how do you characterize properties of networks. And then we will talk about what kind of models can we use to generate realistic networks. Okay, so that's the plan for today. So the first question is, what are the properties of networks? Or how could I measure a graph or characterize the shape of the graph? And I will show you 4 different characteristics of graphs. First we will define them, and then I'll show you a real network, and we will measure them there, and then we'll see whether we should be surprised or not. But so the 4 important characteristics are the degree distribution, something that characterizes the distribution of shortest path lengths in the graph, something that is called clustering coefficient, and then the distribution of connected component sizes. And what I will be doing is most of these definitions I will present in case of simple undirected graphs, but they can easily be extended to directed graphs as well. And wherever these extensions are interesting, I will mention them explicitly, but sometimes I may not, because it's kind of clear how you could extend this. So the first thing that is important, and it will kind of pop out in the future lectures as well, is this notion of a degree distribution, which is simply just asking, if I'm given a graph, I want to plot a histogram of how many nodes have a given degree, right? So if I have this graph here on 10 nodes, then for this graph, this would be a degree distribution histogram, where on the x-axis I plot the degrees, and on the y-axis I plot how many nodes or what fraction of nodes has that degree. So this would mean that 60% of the nodes in this graph have degree 1. And this graph should have 10 nodes, and 6 of them should have degree 1 if I counted correctly, right? And then there is 10% of the nodes with degree 2, because there should be 1 node with degree 2, and that's this guy, and so on and so forth. And I can now start asking, what is the shape of this histogram? Okay, so that's what's called degree distribution. If you are in a directed graph, then you would have 2 histograms, a histogram of in-degree distribution and a histogram of out-degree distribution, right? Because now every node has an in-degree and an out-degree. But in an undirected graph, it's one simple histogram that you can normalize by the total number of nodes, or you just plot the counts themselves. Okay, so that's called degree distribution. First important property. Second important property is trying to characterize the distribution or some kind of notion of paths in the graph. So to define, path is a sequence of nodes where nodes in the sequence are linked to each other, right? So again, if I have my little graph down there, this would be an example of a path where there is an edge between A and C, and there is an edge between C and B, and an edge between B and D, and so on and so forth, right? So this is now, some path in this graph. Okay, so that's a notion of a path. It's basically a sequence of nodes that can be visited by crossing the edges. And now what you can do is, if you have a graph, you can define this notion of a distance. And the way you define the distance is to say, what is the shortest path length between a pair of nodes? Sometimes they call this also geodesic distance. And this is essentially just what is the smallest number of edges I need to traverse to get from one node to another. Right, so if I have my little graph here and I say, what is the path length between nodes B and D? It is 2, because I have to traverse the shortest number of steps or edges I need to traverse to get between the 2 nodes is 2. If my graph is not connected, or it's disconnected like here, then the shortest path distance between nodes that are in different connected components is defined as infinite, or it's kind of undefined, right? There is no way for me to get from node X to node A by traversing edges. So this is in undirected graphs, right? And then in directed graphs, the definition is the same, but now the path has to obey edge directions. So what does this mean? That, for example, the distance between, for example, here I have between B and C is 1, because I can just traverse the edge, but the distance between C and B equals 2 because I go this way. Right? And what is the consequence? The consequence is that in this case, distance is not symmetric, right? It's closer to get from B to C than from C back to A. And of course, there's no way to get from D back to C. So I would define this distance as infinite as well, right? Because I'm in a directed graph. Sometimes what people do is they just transform the directed graph into an undirected graph by kind of dropping or ignoring edge directions and then characterize the path distance, okay? And now that we know how to measure a distance between a pair of nodes, now people define what is called diameter of the graph. Yes?
So does the definition of distance hold in weighted graphs?
Great question. So how would you generalize this to the weighted graph? A definition of the distance in the weighted graph would be what is the minimum amount of edge weight that I need to traverse to get from one node to another, right? So that may not be the shortest in the number of edges you traverse, but it's the smallest possible sum of the edge weights that gets between the two nodes, right? And there are elegant algorithms to do that, okay? Good point. But all of these things can be extended in many different natural ways, as we just saw from the question. Okay, so now I know how to measure two things, a pair of nodes. Now I want to quantify a diameter, kind of how big is the graph, right? And the diameter, how it's mathematically defined, it's the maximum shortest path length in the graph. So it's actually the distance between two farthest nodes in the graph, right? So it's the shortest distance between the two farthest nodes, okay? And this is well defined, and it basically tells me that for any pair of nodes, this is the upper bound on the number of steps I need or the number of edges I need to get from one to another. When you work with real graphs, this diameter definition is not so useful because it's very fragile, right? You can have a graph that is kind of massive but really well connected, and then you have a string of edges, kind of a little string, a little tentacle down, and that will totally skew your diameter. So what people prefer to do is, for example, compute the average shortest path length. So this would be if you pick a random pairs of nodes in expectation, what do you expect the distance to be? So the way you would do this is to say, let me go over all pairs of nodes, ask what is the shortest path distance between that pair, and take the average across all pairs. Now, what do you do if the graph is disconnected? What essentially people do is they would essentially skip that pair of nodes or consider their distance to be 0. But essentially, most often people will just assume the graph is connected or only do this computation over the connected components of the graph. Because if you consider the two nodes into different components, this could be infinite, and then everything is off. Okay, so that's what is the network diameter. And then I have two more to show you. The second one, the motivation really comes from social science, and this metric is called clustering coefficient, and it's essentially only defined for undirected graphs. And the question that it tries to answer is how connected are one node's neighbors to each other, okay? So the idea is that for every node I, we are asking its neighbors, its friends, how much do they know each other, right? So if you say, this is the node I'm interested in, so this would be the node that has very high clustering coefficient because all of its 4 friends are connected to each other. And this would be the same node with degree 4, but now none of the friends know each other, so clustering coefficient is 0, okay? And here is somewhere in between where clustering coefficient is 1/2, right? Some of the friends know each other and some for example, don't, right? So how do you compute clustering coefficient? Clustering coefficient is defined for every node. And essentially the way you understand this formula is E sub I is the number of edges between the friends of node E. So for example, here the number of edges between the friends of node I is 1, 2, and 3. And then this 2 times divided by k sub I times k sub I minus 1, this is really divided by k choose 2, right? This is the total possible number of edges between k nodes, and that's the number of edges that we realize. So essentially we are asking, out of all possible edges between the friends of node I, how many of them exist? What fraction of them exist? Here, all of them exist. here none of them exist, and here half of the possible edges exist, right? There is 4 choose 2 possible edges between these 4 nodes, and 3 of them exist, right? 4 choose 2 is 6. It's 4 times 3 divided by 2, right? So this is 4 choose 2, and that's 3, and that's why I get a half, okay? And then for the entire network, you can say what's the average clustering coefficient of the network. You just compute the average over all the nodes. Generally, again, clustering coefficient is undefined if the node has degree 2 or 1. So generally, you would skip those nodes. That's the idea. Here I have another example where I tried to compute some clustering coefficients for different nodes, and the average clustering coefficient for this graph would be 0.33. So this means that about a third of random nodes' friends are connected to each other, right? And what we see in social networks, this clustering is very high, right? That essentially people who are my friends tend to know each other, right? That's what this do. And then the property number 4 that I want to talk about is how connected is the graph, right? And essentially how you quantify this is to say what is the size of the largest connected component. So how many nodes are in the largest connected component, right? What fraction of the nodes of the graph are in the largest connected component? And then you can talk about the largest weakly connected component, largest strongly connected component if you are in a directed graph. But in a non-directed graph, you just say how big is the largest connected component of the graph. Okay? So to summarize, I explained 4 things. We talked about this histogram of degrees called degree distribution. We talked about trying to estimate the diameter of the graph through the average shortest path length across the pairs of nodes. We talked about this concept coming from social network analysis called clustering coefficient. And then we also talked about trying to estimate how connected is the graph in terms of connected component sizes. Okay? So now with these things, what I want to do is I want to show you one large network, and I want to show you the measurements in terms of these 4 properties on that large network. And I was actually, I did this when I was a student. I was interning at Microsoft, so they had this big network I could play with. Okay? So the network came from this tool Microsoft has. Now I think they renamed it, but it was called Microsoft Instant Messenger, where you could go and message other people. Think of it as iMessenger or WhatsApp, basically essentially the same, right? And at that point in time, they had, if we look at 1 month of activity of this service, around 245 million people actively used the service. And in 1 month, 180 million people actually engaged in conversations. So they exchanged messages. And there was about 1 billion conversations a day, many more billion messages. So 30 billion conversations, and 255 billion messages exchanged over that 1 month period, right? So the first thing you can do is you say, where do these users come from? Right? And here the color, red is high and blue is kind of low, is where the users come from. And you see it's kind of the United States. You see kind of the shape of Africa. You see that there is no one in North Korea, things like that, right? So these are the things you notice from just kind of plotting where the users are. But what are we really interested in is not about this geography. We are really interested in the network. Right? So what will we do is we will go and compose a network, and the network will have 180 million nodes because these are the people who engage in conversations. And the question is, how do we connect people? How do we create edges? At the end, we'll have 1.3 billion edges, but let me show you how we decided to create a network. Right? The way you can think of this is essentially as this kind of multi-graph with 2 types of edges. You know who is on a contact list with whom, and then you also know who exchanges messages, right? So this would mean that these two ladies, they are in contact and they exchanged, let's say they had 2 conversations during 1 month, right? And what we decided to do is to say, let's create an edge between a user if they exchanged at least 1 message in this 1 month period. And that gave us this 1.3 billion edges, right? So for example, in our graph, there would be no edge here because these two people are not, this is not they are not clones of each other, okay? But these two people did not exchange messages, okay? So there is no edge, but there are edges here, wherever is at least one blue line, okay? So now we have a graph. So let's look at the degree distribution. So here is the histogram of the degree distribution for this graph, right? And it looks like a kind of a funny histogram, right? It's basically, what does it mean, right? So here I have the degree of the node, and here is the number of such nodes, right? The count, right? And what you see is all the data is kind of just along the axis, right? So basically it seems there is a super huge number of people who have very small degree, and then there are single people who have very high degree, right? It's very hard, like, I don't know if you've seen this type of histogram before, right? So it looks kind of useless. But what happens if you take the same data, but you change how you plot the data? You don't plot it on linear scales, but you plot it on logarithmic scales, then actually good stuff emerges, right? So this is now exactly the same data, just this is now logarithmic, and this is now logarithmic, right? So this is 10, 100, 1,000, 10,000, right? And you know, this is 10 people, 100 people, all the way to 10 million, 100 million people, right? And what do we learn from this is that majority of the people has very small degree, right? Like number of people with degree 2 is, I don't know, 20 million or so, right? But if you say how many people have degree, I know more than, this is like 600 or so, it's basically these are just single people, right? There's one person with that degree, right? So this means that degrees are amazingly skewed in a sense that most of the nodes have very low degrees, like orders of magnitude more nodes have very low degrees, and very few have very high degrees. Okay? So this is a degree distribution. That basically, if you plot it, it looks like this. On linear scales, if you just look at the histogram, if you create the histogram in this logarithmic space, then kind of a pattern emerges. And we'll talk later in the quarter why is this is kind of a very important property and what does it mean. So in terms of clustering coefficient, here I'm plotting it for every degree. What is the average clustering for the nodes of that degree? But essentially, if you compute now the average clustering over the entire graph, the clustering is 0.11, right? So about 10% of one's friends know each other, okay, or are connected to each other. Right now, it's not clear whether this is big, is it small, is it impressive, is it not impressive? It's just a number, 0.11, okay? And then the last thing is about, is this network connected? How big are connected components in this graph? And here's the plot. Again, it's on logarithmic axis. And basically what you find is the following, is that there is one component of size, basically 10 to the 8. So this is 10 million. This is basically 100, this is 200 million. So there is one component close to 200 million in size. And then there are other components that are tiny, that have less than 100 nodes. And there are a few nodes up there that are just talking in pairwise. There's about 1 million of people who just talk to another person, and it's an isolated component of 2, right? But what do we learn? We learn that this communication network is extremely well connected, right? The world is connected. It's 99.9% of all the nodes are in this connected component, and then there is a few very small, tiny connected components, right? The difference between the largest connected component and the second largest is 10 to the 6, right? So the largest connected component is 1 million times bigger than the second largest connected component. So essentially, for all practical purposes, there is one connected component and the rest are some little leftovers. Yes?
Why are you looking at weakly connected component size?
Can you repeat?
This is an undirected graph.
Correct.
So why are we looking at weakly connected component size?
Sure, it's the same.
Okay.
Ignore, yeah. Probably because I also was looking at the directed graph, but I did not include that. Okay, so this is undirected. And then the last thing is, how about the shortest path distributions, right? If you say I have people across the world, how many steps does it take from one person to another person via the shortest path, right? And given that the world is big and it's a lot of people, maybe it takes many steps. But what is interesting is that it doesn't really take too many steps. This is the number of steps between, or the shortest path distance between a pair of nodes, and the y-axis is number of such pairs. what do you learn? You learn that, and again, notice this is the logarithmic axis, while this is linear, right? Majority of the people can be reached in 5 hops. And yes, there are a few people who are far apart, like 30. The point is majority is very close to each other, right? So if you wanna get to the Queen of England, it doesn't take you, 30 steps to get to Queen of England through your friendships. It will probably get you 3 or 4 and you'll be there, right? So the world is amazingly well connected. And if you say what's the average shortest path length, it's 6.6. And 90% of all the pairs of nodes can be reached in less than 7 steps. In less than 8 steps. So in 7 or less, right? And just to show you a way how this looks like, if you take a random node and you ask how many neighbors are at step 1, how many do I see at step 2, at step 3, this is basically the frontier of the breadth first search as you go. So you see it goes from 1 to 10 to 80 to 400 to 8,000 to 3 million, 28 million. At 7, you are at 80 million, and then it kind of starts to decay all the way down to somebody who's to 3 people who are 25 steps away from you. Yes?
For the step 1,
yeah?
when the step is 1, it should correspond to the connected component.
No, at step 1 is the degree of the node. Right? Step 1 is I'm here, I have 10 friends, so at step 1 I see 10 people. And then at step 2, I see how many friends of friends do I have, and that's 80 in this case.
Yeah, what I mean is it should correspond to the clustering coefficient for step 1.
Not really.
Degree.
Not really. It will correspond to the degree, the number of edges the node has. Okay? So let's just summarize. What did we learn? We learned that the degree distribution has this weird kind of axis-aligned shape, and the average degree, we have about 200 million nodes, 1.3 billion edges. So the average degree is around 14. The average shortest path length is 6.6. Clustering coefficient is 0.11, and the graph is connected. We have this giant connected component. Okay? So now these are just some numbers. And the question is, should we be surprised? Should we say, wow, this is so fascinating? Should we say, totally boring, let's go home? What should we say, right? So the question is, are these values expected? Are they surprising? And the only way for us to answer this question is that we need a model. And just to show you, this was now a communication network of the entire world for 1 month. I show you that in a very different domain, in biology, if you take a protein-protein interaction network with 2,000 nodes and about 3,000 connections, you see similar things, right? This is the degree distribution on logarithmic axis, and you see how it kind of looks similar what we have before. Here is the distribution of shortest path lengths, right? Something very similar to what I showed you for Microsoft Instant Messenger. Here, the average shortest path length, I think, is 5.8 or something like that, right? And this is the distribution of clustering coefficient, right? So for a network coming from a very different domain, average degree is about 3, shortest path length is 5.7, clustering is 0.12, my network had 0.11, and connectivity is that 81% of the nodes are in the largest connected component, right? So even kind of, I guess, thinking as a physicist, these things look about the same order of magnitude what I had here, right? It's kind of roughly the same. It's not orders of magnitude off, right? It's about large connected component, 80%, clustering coefficient 0.12, shortest path length 5.1, 5.8, and the degree, I think, was 3 or something, right? So it's about the same, even though the network is totally different, smaller, and so on. So now what I want to do is I want to show you a first, easiest, simplest graph model that's named by after 2 famous Hungarian mathematicians, Paul Erdős and Rényi, and it's called Erdős-Rényi random graph model, or some people would call it Poisson random graph model. Let me tell you how this works. It's the simplest way to generate the graph. There are 2 variants of this model. Something that in mathematics they call or label as GMP, and then there is another variant that's called GNM. And essentially, what does GMP stand for? It says this is an undirected graph where I have n nodes, and each pair of nodes is connected independently with probability P. So this model has two parameters, number of nodes and P. Right? So the idea is I throw the nodes on the table, I pick a pair, flip a coin, with probability P, coin says yes, and I connect them. And then I pick the next pair, flip the coin, and connect. Okay? So that's one definition. And another definition that's very similar is GNM, where N is the number of nodes, but M is the number of edges. Right? So up there, the number of edges is a probability. The total number of edges is kind of a probabilistic event, while here the total number of edges is exactly n, that I place kind of uniformly at random among all pairs of nodes, right? And the question is, what kind of networks does this simplest possible model of networks produce, right? What is important to know is that for the GMP, as well as GNM, the network is not uniquely determined, but it's a result of a random process, right? So if I pick some parameters N and P and generate graphs, these graphs will look different, and they will also have a different number of nodes, a different number of edges. They will all have the same number of nodes, but they will be a bit different because all these edge events are stochastic random events, right? So what we will do next is I will show you properties for this particular graph model. The important thing is that this graph model is so simple that you can actually analyze it, and you can prove what kind of properties these graphs will have. So you can go and analyze what will the degree distribution look like, you can analyze what will be the clustering coefficient, and you can also analyze whether the graph will be connected and what will be the shortest path length. Okay? And I will show you now these values. And if you are interested in more, I can point you to actual proofs. I won't be doing actual proofs, even though they're actually quite simple. Okay? So the first fact is the following. The first fact for a GMP, so for a graph with n nodes where every pair of nodes is connected independently with probability P, is binomial. The way you figure this out, you say let P of k denote the fraction of nodes with a degree k, then you could ask, how many nodes do I expect to have the degree k? Right? If you say I have a node, then there are n minus 1 other nodes. And out of these n minus 1 other nodes, I have to select k of them. Right? So there is n minus 1 choose k ways I can select k nodes out of n minus 1. And then for these k nodes, I have to create a connection to each one of them. So there is probability of me connecting to one of them is p, but because there is k of them is p to the k. And then to all the other nodes, I must not create a connection. Probability of not creating a connection is 1 minus p. And how many of such nodes are there? There is n minus 1 minus k. Okay? And that's now the probability that a given node will have degree of k. Okay? So, as I explained, this is how many ways are there to select k nodes out of n minus 1. This is the probability that a given node will have k edges, and then the probability that the rest of the edges will not be there. Okay? If you look at this, this is exactly what the definition of a binomial distribution is. How does binomial distribution look like? It's essentially a discrete analog of a Gaussian distribution, right? So it has this nice bell shape. Okay? What should you notice? You should notice that what I showed you for the messenger network was nothing like a bell shape. It was something much more skewed along the axis, not some nice bell-shaped thing. Okay? So there are two important consequences. The first thing is, what's the mean of a binomial distribution? It is just p times n minus 1. Right? So basically, the mean or the average degree will be p times n minus 1. And here's the expression for variance. And the reason why I'm showing you this expression for variance, because you can then ask, how does the variance change as a fraction, as a function of the average degree? So you can kind of measure variance in terms of the average degree. And if you compute this, you see that this ratio has the value of 1 over square root of n. So what does this mean? This means as the graph increases, size of the graph increases, this ratio will go to 0. Right? So what does this mean? This means that as the size of the graph gets bigger and bigger, the distribution will kind of narrow. Right? And essentially what this means is that if you think the graph size to be infinite, you can think of it that all the nodes have the same degree of average degree, which is k bar, which is p times n minus 1. Right? So this is essentially a graph where everyone will have the same degree in the limit. Okay? Or at least you can think of it that way, because the variance will in some sense be getting smaller and smaller. Okay? So that's the first property. Second property is clustering coefficient. Right? I have the formula for clustering coefficient above, and it's actually very easy to prove what will be the clustering coefficient in this GMP. And the only thing I have to remember is that edges in this GMP model appear independently with probability p. Right? So what do I need to compute? I need to compute that E sub I, right? Number of edges between friends of a person. Right? So how do I do this? Basically, I just say, what is the expected number of edges between k people, right? So the possible number of edges is k choose 2. This is k times k minus 1 divided by 2, right? K is the degree of the center node. So there are k choose 2 ways to select pairs. This is the total number of edges possible between k friends. And each of them happens with probability p. So the expected number of edges between them is p times k choose 2, okay? Where k is the degree of the node. Great, that's what we say. So now I can just take this E sub I, the expected value, plug it in the equation above. And if I do this k times k minus 1s will cancel, and I get that the expected clustering coefficient of some random node I equals p, okay? Which is the probability of an edge. So what is p? P is the average degree divided by n minus 1, right? Right? And if I simplify a bit, this is average degree divided by the size of the graph. Okay? That's my expected clustering. One way to think of this is that basically this will be small. And if you think of it the other way, if I keep average degree constant but generate graph that is bigger and bigger, then k bar will be constant, but n will get bigger and bigger. So this ratio will get smaller and smaller, which basically means that if I generate random graphs where every node has with constant average degree, the clustering will go to 0. Okay? So what did we learn so far? So here is what we learned so far. We learned that degree distribution follows a binomial. We actually derived an expression for the value of the clustering coefficient. Now I need to show you two other properties. One is the shortest path length, and then I'll give you some fact about whether these graphs are connected or not. To prove the shortest path length, I'll just give you a bit of a flavor. How do you need to think? And the way you need to think is that you define this notion of an expansion, which is basically you say that a graph will have expansion alpha if for any subsets of nodes, the number of edges leaving that subset is greater than the alpha times the size of that set. Okay? So essentially what we are asking is, if I pick a random set of nodes, how many edges are going to leave that set, right? The way you can essentially think of this is the following. You can think of it is that alpha is the minimum over all subsets of edges where you take the size, the number of edges leaving that set S divided by the size of S. Now you will ask me, why do you have this funny minimum of size of S, comma, minimum of the entire set of nodes minus S? The reason why you need to do it this way is that you take whatever is smaller, right? What do I mean by this is, if you think that S is, the size of S is less than half of the nodes in the graph, then you can just divide by the size of S. This is just kind of to prevent the metric from cheating itself, okay? So this is what alpha is, right? The way you can think of this is, if I split the nodes that belong to S and the ones that don't, the question is how many edges point across, And it turns out that that random graphs have high expansion. So there is a lot of edges between any set of nodes to any other set of nodes, right? Notice that this expansion property is defined over all sets of nodes, right? I'm trying to find the worst set of nodes, okay? So this is a dense slide, but the following is true. First is that a random graph with n nodes and expansion alpha, then if you have a graph with this property, then for all pairs of nodes, there is a path of length log n divided by alpha. Okay? Why is that the case? Because the case is that if you have some expansion, then when you start with some set, a single node, you expand to some number of nodes, and then you again expand to the next number of nodes. And if at every step my number of nodes that I see increases for a factor of alpha, then it will take me a logarithmic number of steps before I will visit all the nodes in the graph, right? So that's essentially the intuition, is that I'm basically having like, you can think of this as almost like one way to think of this is as almost like building like a binary tree, right? If every node has 2 friends and every of the friends has 2 other friends, then at every step I'm kind of doubling the number of nodes I visit, so I can only double this log number of steps before I have visited all the nodes, right? So what is this precise expression for the random graph? When n times p is between log n and some constant c, so mp is the average degree, then the diameter of the graph is of the order log n divided by log np. So you can just think of essentially log n is what matters. Now, why do I have this log n here and that constant? So I need to have some reasonable degree to have small diameter. And when the degree increases log n, I will essentially have a graph with constant diameter, which means a fully connected graph. So this is why I have these things this way. Generally, average degree is like 5 or 10, so it will be kind of less than log n. This is what the diameter is. So diameter, what do we need to think about is logarithmic in the size of the graph, okay? So it should grow logarithmically with the size of the graph. And then this is the picture I wanted to give you about the expansion, right? If I start with s nodes, then I will have alpha times s edges pointing out. So this I will get some newer set of s nodes that will be bigger than the previous one. And this is the way kind of how breadth first search will work. And all I care about is how often do I need to do that until I reach all the nodes of the graph. And the point is I can do this only a logarithmic number of steps before I run out of nodes, which means that in the logarithmic number of steps, I must have been able to visit all the nodes. This is kind of long way to explain this, but here is the example, like a simulation experiment. Here is, I'm generating graphs where n times p is constant, so the average degree is constant. And here is the size of the graph versus the diameter, the average shortest path. And notice how this has this kind of logarithmic shape, right? After a while, basically, it increases very, very slowly. And I can be generating bigger and bigger graphs, but the diameter is just very slowly increasing, okay? So what did we learn is that the random graphs have diameters that are, in some sense, small. They are logarithmic in their size, or they grow logarithmically with the size, right? And I'm ignoring constant factors and things like that. And then the last thing I want to say is, when is the random graph connected? And it turns out there is this beautiful result that basically shows that random graph will get connected when average degree is greater than 1. So here is again, a computational experiment. X-axis is average degree, and y-axis is the fractions of nodes in the largest connected component. And you see how largest connected component, as I increase average degree, is very tiny. And then once I cross 1, the largest connected component size starts to increase. And there is this phase transition where basically before graph is essentially disconnected, I cross the average degree 1, and this giant connected component starts to form, right? So our average degree is somewhere here. So our graph is connected, random graph. let's say at average degree 10, will also be quite well connected, or the largest connected component will be quite large. Okay? So let's now compare to see what did we learn. So in terms of degree distribution, we saw that the two couldn't be more different, right? The random graph will have this type of bell-shaped degree, and my MSN network has just like degrees along the axis of the histogram. Then for the shortest path length, we saw that MSN has about 6.6, and random graphs have about log n, which is about kind of seems right. It's small. It's exponentially smaller than the size of the graph. So let's say that this looks good, right? Then we said clustering coefficient, right? Clustering coefficient in our graph, the MSN graph had 0.11. If you ask, if you enter the average degree, which was 14, divided by 180 million nodes, then an equivalent random graph would have clustering of 8 times 10 to the minus 8, right? So we are about 6 orders of magnitude away, right? So obviously not good, right? For the diameter, log base 10, for example, of 180 is 8.2. So it's quite close. So we can be happy. It's the right kind of order of magnitude. And then in terms of the connected components, we said 99.9% of the nodes are in the largest connected component. What I showed you a few slides ago is that this large connected component will exist when average degree is greater than 1. Our average degree is around 14. So in a random graph, largest connected component will exist as well. Okay, so what did we learn? We learned how to characterize networks. We learned the simplest possible model of a random graph model. And now we kind of know what to be surprised about and what not to be surprised about, right? So, you know, maybe at the beginning we would be surprised that it's only 6 hops that separate random people. This is where this notion of the small world or 6 degrees of separation comes from, is exactly from this, right? And we'd be like, wow, this is so surprising. And it turns out it's not surprising at all. If you just create a random graph, you get this for free, right? For example, degrees seem much more interesting. What also seems interesting is this difference in the clustering coefficient, right? Here we have a lot of clustering. This thing essentially has 0 clustering, right? And then the connectivity, which again would sound very surprising if you would tell someone, it doesn't really seem to be too surprising, right? So by basically having this model, we now can make sense out of the numbers and measurements we did. So that's kind of the meta point I want to make, right? So we showed these 4 properties. You know, is the random graph model realistic, or what are the problems with it? You know, the degree distributions differ. Basically, it assumes everyone has the same number of friends. This giant component does not emerge through this kind of phase transition that I showed you, and they have no clustering coefficient, right? So are real networks random? Like the random graph model, the answer is simply no, right? So it's not the case. But, right, even though this GMP model is wrong, so why did we spend so much time on it, right? The reason is because this is the simplest model, and it's kind of a reference model to judge any network against, to say, should we be surprised about something or not? It's also kind of showed how we can calculate in a mathematically rigorous way many different quantities, and how do we then can compare them to real data. And it kind of helps us to understand what properties of the graph are a result of some random process, and what other properties are maybe not result of the random process, right? So even though this model is kind of wrong, it's very useful, right? So this is what I wanted to say about the GMP model. Are there any questions? Right? So if not, what I will do is I will now show you one more model, and then Michele will take over and show kind of this beautiful mathematical way of generating very interesting self-similar graphs. Yes, go ahead.
So if the network did match up with the GNP, would you just say, hey, this MSN messenger network it's random. There's nothing significant here in this information. If you were to, just do a random probability, you get the same thing.
Great. So if GMP and messenger network would match in all the properties, then I would say the human social network is essentially random. We make friends with random people who make friendships with other random people. That would be a super cool social science discovery. But the world is a bit different, right? But it's interesting, right? Like your question is great because why is this interesting? Because the 6 degrees of separation based on this model is nothing to be surprised about, right? Being surprised that the world is small is like the most expected thing ever, right? Like the simplest model gives it to you for free, right? But there are other properties that this simple model doesn't give you, and maybe we should be more surprised about those properties, right? So it kind of gives us a reference point to judge data against, right? And one thing to notice, I emphasize the messenger network, but if you remember when I showed you that biology network, it's very similar in terms of clustering, shortest path distance, degrees. So the biology network is also not random, right? It's not that random proteins come and hang out with other random proteins, all right? So now what I want to do is I want to show you the next flavor of the model that kind of builds on this random graph model. And this model is called the small world model. And the point of this model is try to reconcile this notion of clustering and shortest paths, right? It's clear if I have random network, shortest paths in the network will be very small. So that's great. But this would assume that we as humans, we have random friends all over the world, right? But we humans, we make friendships by physical interaction, right? So I mostly have friends where I live, right? And those friends are friends by themselves. So this friendship graph is not random, but has a lot of clustering, right? And a structure that would have a lot of clustering would look like this. Right here, for every node, it has some friends, and these friends know each other as well. So these kind of grid structures have very high clustering coefficient, right? And social networks have high clustering coefficient. But what is problematic with this picture is that now the diameter is very large here as well. So the question is, can I have high clustering, but also low shortest paths? Because it seems that social networks have both, right? They have a lot of these kind of redundant connections that don't bring down the diameter of the graph, but they still have small diameter. So the question is, why is that? How could I have both? So as I showed you in the messenger network, the clustering coefficient between the messenger network and the random graph was 7 orders of magnitude off, right? So it was our error was 10 million times, right? So here are some other networks that I took that, for example, compare the shortest path length and the clustering between a random graph with the same number of nodes and same number of edges versus the real graph, which are labeled as H actual. Okay? And one is a network created from IMDb, so Internet Movie Database, where every actor is a node, and 2 actors are connected if they co-appeared in a movie. So it's a actor collaboration network. If you say what's the shortest path, their average is 3.6. You ask what it would be in a random graph, it would be 3, very close, but a bit less. What's the clustering coefficient? 0.8. What would be in the random graph? 3 orders of magnitude less. Now, this is the power grid, which is basically a graph telling us how different power plants are connected into a grid. Here, the diameter is bigger, but random graph would also have bigger diameter. Clustering, again, or 10x difference. And then this is a network of neurons from a C. elegans swarm, shortest path length, and then clustering. And again, 20 times or 5 times the difference, right? So the point is that while random graphs have about the same shortest path lengths as real networks, they have far lower clustering. And the question is, why is that? can we get the two to match, for both of them to match? So here's in some sense, the controversy, right? The controversy is the sequence of this expansion property I showed you before is that the diameter is small, right? So essentially, this is the smallest diameter you will get if you keep the degree constant, right? So if you want to have the shortest paths to be short, the best thing to do is to have a random graph. That's great. But networks, social networks in particular, have a lot of local structure. This notion of what social scientists call triadic closure, that friend of a friend is also my friend, right? So if you are friend with Michele and Michele and I are friends, then the two of us will likely be friends as well. And this means that the clustering will be high. But if clustering is high, then the network must look something like this, right? It has a lot of these redundant edges that connect friends of friends, so they don't contribute to making diameter small. So the question becomes, can I have both? Can I have a lot of this type of triadic structures, these triangles of connected nodes, but still have small diameter? And this model was invented, I think, exactly 20 years ago, in 1999, where people were asking, how could a network with high clustering also be small world, meaning have small diameter? And the question was, can I have the two at the same time, right? Can I have kind of, here I show the nodes on the ring, and I connect nearby nodes, but then also kind of friends of friends. So this would now have a high clustering coefficient, but also high diameter. And a random graph on the same set of nodes would have low diameter, but also low clustering. And the question is, can I have high clustering, low diameter, right? And the solution is a very elegant model, which says, let's start with a low dimensional regular lattice. So in our case, this would be nodes on a circle where every node links to the two friends next to it, plus friends of friends. Okay, so this will now have high clustering coefficient because basically this has clustering coefficient of 1. Okay, but what will we do then is we will have this rewiring phase where we will introduce just a bit of randomness. What does this mean is we will pick random pairs of nodes and we will rewire their connections. So this means that for each edge with a small probability p, we will rewire the other endpoint to some other node, right? So for example, if I pick these two nodes, this node, for example, I would take one of its edges and rewire it somewhere randomly. And then I would maybe pick another node, take one of its edges and rewire it randomly, right? And I will do this for only a small fraction p of all the edges. And I can kind of keep doing this for every pair or every edge. I flip a coin and I decide whether to randomly rewire it or not. And the question is, what kind of graph do I get? Okay, so here is what kind of graph do you get, right? You know that when p is 0, we will have high clustering and high diameter. And we know when p equals 1, which means every edge gets rewired, we'll have low clustering and low diameter. But it turns out that when I'm somewhere in here, in some good range of p, I will maintain the high clustering, but I will also get low diameter. So it means these random edges, there will be just enough of them to collapse the diameter, but not too many of them that they would collapse the clustering. And I can now show you how the results of this computational experiment, right? So on the x-axis here, we have the probability of rewiring, right? Y-axis here is average clustering coefficient, and on this side is average shortest path length, right? When p equals 0, we have high clustering and high diameter. When p is very large, we have low clustering and low diameter, right? This is a random graph. This is our circular lattice graph. But notice that in some parameter region here, we have both of them at the same time, right? We have low diameter, but the clustering still remains high, right? So the point is that in this case, essentially, we need just a few of these random shortcuts to collapse the diameter, which seems to be a very fragile property, while the clustering still remains robust and high. So what does this teach us about social networks? It teaches us the following, that yes, we have high clustering and we have low diameter, because most of the friends we have are local and they know each other. But we also have a few colleagues who live in other countries, other continents, and so on. And we only need a couple of those random colleagues in some way, this kind of long-range edges, to collapse the diameter of the world's social network. Right? So this is kind of what we learned. We learned that the human social network is very local in terms of edges, and that you need very few of these long-range friendships, this kind of weak ties to distant continents and countries, that they just collapse the diameter and basically bring down the degree of separation of the network to be something very small. And this is basically the model that illustrates that. Right? So the question we asked was, could you have a network that has high clustering and has small diameter at the same time? The answer is yes, and all you need to do is to add a few random links, and that's it, right? So this small world model was developed by two mathematicians from Cornell, Duncan Watts and Steve Strogatz. They basically provided the insight on the interplay between the clustering and this small world low diameter property, and captures the structure of many realistic networks, accounts for high clustering in real network. But for example, what it doesn't solve yet is the degree distribution. It doesn't say anything about the degree distribution. So that still remains unsolved. So with this, I will finish. And now Michele will tell you about how to build real graphs in a bit different way. Okay? 30-second break. Okay? Thank you. So, okay, thank you.
No problem. Okay, exciting. This is like the car races, you know, where they swap the pilots in the pit lane. So, exactly. All right. Okay. All right. By the way, we will put this paper in the reading list. It's a beautiful read. It has, I think right now, 40,000 citations, which means it's one of the most famous papers in network science. So I strongly recommend you to go and take a look at it. Now, let's jump to the last topic of today's lecture, which is Kronecker graph models. And I'm going to tell you how to generate basically graphs following this model. It's a very beautiful model, but in terms of the mathematical theory behind it, it's very concise and elegant. But at the same time, it also helps us to generate very large graphs. And to the extent that you will see from the way in which it's structured, it's embarrassingly parallel. So a lot of challenges on how to generate large graphs in high-performance computing have been won through this technique. Okay, so that's why we want to cover it today. Now, what is the key idea behind it? What we want to do is we want to generate this nectar structure recursively, okay? And the intuition is the self-similarity one. So think about one of a big social network. The way in which people establish friendships in different countries is pretty much the same. Similar culture, similar ways to establish friendships. Therefore, you can expect in a very large graph to have some subgraphs that look pretty much the same. And this is the intuition behind the Kronecker graph. So we take this initial graph, our initiator matrix, and then we're going to try basically to replicate it multiple times until we reach a graph of the size that we want. Okay? So this is like one step. We go from our, oops, my animation is not working. So we go from our initial graph to this first step of recursive expansion, okay? So you can recognize this initial one, replicate it 3 times, and then it's connected on each layer. So how do we bring this idea to something that scales to millions of nodes? This is the initial matrix K1 that we're going to be using. So this is an adjacency matrix, okay? We have self-loops, we have these nodes connected to each other, and we start from a small one of size 3 rows and 3 columns. And this is our second step, okay? So we go to our K2. I'm going to explain in a bit what is the Kronecker product, but the idea here is it's very intuitive. You can think of basically replacing one element in our initial matrix with the full matrix K1 that we have just seen, okay? So you take the elements of K1 as weights, as scalar, and you multiply this weight with the matrix, and you decide if the matrix will appear in there or not. So now the K2 is 9 by 9. We can go to the next step. So K3, then it will become 81 by 81, and so forth. And you would see that each quadrant, each tile, the shape of the adjacency matrix looks exactly the same, okay? So basically, if the intuition is if our K1 captures some sort of regularity in our graph, let's say the way in which people establish friendships, then we can replicate these multiple times, and we can have this graph growing. Now, to go back to the argument that I made before, so how can we make this scale to large clusters? You can think of basically subdivide the work among different nodes, among different servers, and then at the end you will merge the graph together, okay? So it is one beautiful aspect of this model. Now, let's see again what is the Kronecker product. So this is the only piece of theory that is going to be required to understand how we generate graphs. Yeah, question.
Is this the same as the tensor product?
Yes, pretty much, yeah. So the idea is the following, basically, and I'm going to try to make it as simple as possible. You start from your matrix A, and what you do is you turn each element of your matrix A into a weight, into a scalar. And then you're going to use that to multiply B. So B's will become our tiles, and A's are our weights. The example that I've just made before is there are square matrices, and we were doing the Kronecker product of the same initiator matrix. It doesn't have to be the case, okay? So the matrices can be any size that you want, and they can also be different ones. I'm going to show you later on. But we started from a very simple example. Okay. So this is how we define the product, and let's go into now a bit more detail. So how do we then generate the graph? So once again, we are generating an adjacency matrix here, okay? So the values can be either zeros or ones. So we decide when there is an edge between two nodes or not. And so if you want to generate our matrix K of M, then we're just going to apply the Kronecker product M times, okay? And you can see here that the size of our graph will grow with powers of 2. So this is one, let's say, small shortcoming of the model. But as you can imagine, this is a generative model. So what we care about is that the number of nodes will be pretty much the order of magnitude of what we want to generate. And then usually these generative models are interesting because then we're going to go and analyze their properties and see if they match any real-world model. Okay, so the fact that it generates only graphs with a power of 2 in terms of number of nodes is not such a big shortcoming at the end of the day. Okay, now some examples of how the adjacency matrices will look like when we make this grow up to bigger sizes. So the example on top is a simple star graph plus self loops on each node. So once we repeat this process 10 times or so, this is how our adjacency matrix will look like. It pretty much looks like the game of life if you ever play that. If we take a different kind of K1, then different shapes of our adjacency matrix. Okay, now we don't only want to generate such regular graphs. For instance, what we have seen before in the small world model when we were starting from this very regular lattice, lattices are very easy to generate because they come with a very regular shape, so they can be deterministically generated, but at the same time they don't really capture a lot of real world models. Okay, they don't capture a social network or the way in which proteins interact with each other and so forth. So usually we want to bring some stochastic aspect to our generative model. Okay, and that's what we're going to be doing now by adding this stochastic part to the Kronecker graphs. So how do we do that? It's one simple difference. So when we work with our initiator matrix, rather than allowing only values 0 and 1, the value there can be a probability, okay? So our theta 1, each single cells can range between 0 and 1, okay? And everything else is going to stay pretty much the same. The way in which we compute the kth power of our theta is exactly through the Kronecker product that I just showed you before, okay? And now, once we create this template matrix, then we can generate different instances of a graph. And the way in which we do that is, this is our initial theta 1. These are probabilities. Notice that they don't have to sum to 1, okay? Like each element has to range between 0 and 1, but this is the probability that that edge exists, okay? So they don't have to sum to 1. In fact, here this is 1.1. And then we do the standard Kronecker product, as I said before. So from theta 1, we go to theta 2. So you will recognize exactly the same operation that we were doing before. So you now have 0.5 times 0.5. Here we have 0.5 times 0.2, and so forth, okay? So we build our theta 2, and this is the probability that a certain edge PUW will appear in our graph, okay? So as you can imagine, we can run through this template matrix and produce different instances of our graph, because for each entry in that matrix, we're going to be flipping a coin, all right? So who can see a problem here? Like, everything that I just said hopefully is beautiful and it makes a lot of sense, but there is a problem in terms of performance starting from here. Can you think about it? What could it be? Try to generalize this problem from the toy example that I just made to something much larger. So say instead of having 4x4 nodes, now we have 1,000,000 nodes. What happens here?
You have a huge memory impact.
Great. So first problem is you have a huge memory impact, but then think about it also in terms of runtime. What is going to happen is that you will have to perform 1,000,000 times 1,000,000 coin flips. So that's going to be like a trillion operation, 10 to the power of 12. Okay, so all of a sudden, with the number of nodes growing, then the number of operations that you will have to perform in terms of to instantiate this graph will be quadratic in the number of nodes. Now, think about the network that Jure just presented like half an hour ago, the Microsoft Messenger. There we were talking about 100 million nodes, okay? So the whole selling point that I was making about the Kronecker graph was the fact that it allows you to generate very large networks and that you can parallelize that. But once we move to this stochastic model, now we have this shortcoming that you would have to perform too many coin flips in order to generate one instance of the graph. Yeah, question? Exactly, perfect. Yeah. So I wasn't leaving you hanging like this. So now we're going to fix the problem. Perfect. Okay, so we fix the problem through knowing that in reality, graphs tends to be very sparse. And usually, I mean, a real-world graph has a 1 order of magnitude edges more than number of nodes. So I'm going to give an example at the end. We have like 50,000 nodes and 500,000 edges. So it's not required to flip a coin for each single entry of that matrix. So what are we going to do here? We're going to exploit the recursive structure of the Kronecker graph, okay? And basically, the idea is we're going to drop edges onto the graph one by one. So we decide how many edges we want. So say we have 50,000 nodes as our starting point, and we decide we want to add 500,000 edges in total, okay? So we're going to be avoiding the 50,000 squared number of operations. Rather, we're just going to do 500K operation times some constant. And as you're all studying computer science, you know that we don't care about constants when we do the big O analysis. So that's how we're going to play the trick. So here's the faster way to generate our Kronecker graph. On top, you would see again the way in which we apply the Kronecker product. So we go from our theta to our theta 2. And the intuition here is rather than seeing all these probabilities as the product of the initial weight times the entry in our initiator matrix, we are going to be splitting this matrix into quadrants. So think about when we were playing like the battleship game as a kid. So you split it in quadrants, and then for each quadrant, we're going to be using the probability that the edge might be dropping in that quadrant, okay? So what we do is, okay, we flip a coin for each quadrant, and then this coin will tell us the edge is going to be dropping in quadrant A. And now recursively, we do this operation once again, okay? So we flip a coin here, and boom, we end up in this sub-quadrant D, and we do it one last time, and we are right at the end, and now we can actually insert an edge in that graph. So you might be wondering, okay, what happens now if there are edges colliding? Because before, the initial strategy that we had to generate the stochastic graph model was to go cell by cell and flip a biased coin. Now here, there is a chance that we might ending up in this cell twice. We just reinsert it. It's not a problem at all. Okay, so we just reinsert in case there is a collision. And again, given the argument of sparsity, this happens in very rarely, so less than 1% of the times. Question?
You're saying with a certain probability, you insert it into a certain quadrant, right? What
Exactly.
probabilities are you using for these?
The probability from the initial matrix. Exactly. So it will be biased with that. Okay. Any other questions? Okay. All right. So very easily, this is the algorithm explaining exactly what we are going through. So basically, this operation will allow you to move one in the exact position in the quadrant. So every time you narrow down at one level, you go to the level below, and then you will be moving your cursor to the right cell. And then with the last coin flip, you will decide if you're going to be adding an edge or not in that cell. So let me give you a question.
With this method, we have to decide on a total number of edges to drop in.
Correct.
As previously, that could be random. How do we choose that number?
So basically, it's a great question. The question is, here we need to choose the number of edges that we want to generate. Before, it was all based on the probability. You choose the number given some common sense assumptions, some real world assumptions. So if you know that you want to generate a social network graph, then you will be taking a look at a few other graphs, see what is the ratio between number of nodes and number of edges, and then rely on that and do something similar here. So it's driven by that. And again, it's really the only way to go, because after a certain size, you cannot afford anymore to do the deterministic version of that. Okay. Thanks. Question?
How sensitive is this to the original matrix that you start with?
How sensitive this is from the original matrix?
Yeah.
What do you mean exactly?
The graph that you generate, could it be very different if I started with a slightly different initiator matrix?
Yes, absolutely. So finding the right initiator matrix makes all the difference. I don't have time to go more into detail for this, but for instance, if you just do the generation through this model that we talk about, you will be seeing a node degree distribution that is not smooth at all. So you will be seeing a lot of spikes. And the reason is some terms of these probabilities will accumulate. So you will see here it's a to the power of 3. So some of these probabilities will be all the same. So you will be seeing a lot of spikes in the distribution. And then there are noisy ways of this stochastic model that allow you to smooth it out. So yeah, there are a lot of things that you have to take into account. But basically the idea is, as any generated model, this is much more powerful compared to the small world that we just talked about, because in that case, you were just deciding the lattice and the probability of rewiring. So it's basically a model with 2 parameters. And here on the other side, you have an initiator matrix, you have multiple trade-offs that you have to take into account. So it's slightly more difficult, but it has the power to generate much more realistic graphs. Thanks. Question?
So it looks like this is how you drop a single edge onto the graph. Is there a separate methodology to choose how many edges you should be dropping, or is that some sort of predetermined parameter?
Yeah, so your question is, how do we determine the number of edges that we want to drop in the graph, right? Okay, so it's similar to the question that I was answering before. That is, you're going to be driven by some common sense arguments. Like, for instance, you know that in a social network, you will have 10 times the number of edges compared to the number of nodes, and that's what you're going to be generating. Okay, so, and you can play basically with these kind of parameters. Thanks. Is there a way to learn the metrics? Yes. To make it simpler, there are now deep generating models based on deep learning, where you're going to be learning even more powerful model compared to just learning the metrics. But there has been a lot of work being done after this model has been initially published. We're going to be talking about deep generating models in lecture 10, if I recall correctly. So give it a few weeks, and we're going to show you more than this. But yeah, this was quite groundbreaking when it came out, because again, it allows you to work with very large graphs, and it's an easy model to think of. Any other questions? Okay, so let me show you just last slide. a real-world example and how well this model works. So we took the e-opinion network. It was a relatively old social network where people were sharing opinions and reviews and so forth. So number of nodes is 76,000. Number of edges is 510,000. This is our initial theta 1. And as you can see, basically, the real graph is with the red line, and our Kronecker generated graph is with the green line. And most of the properties of this graph are pretty much matching very closely. So the node distribution, basically the clustering coefficient, or the triadic closure. This is the shortest paths, so the average length of the shortest paths. Even at the level of the spectral analysis that we're going to be seeing in a couple of weeks. So these are the singular values, and you would see that there is some discrepancy, but it's not large enough to claim that the model is completely off. It was, again, for the time when this was published, it was very powerful, and it allows to simulate real-world networks. Okay? So I'm going to end it here unless there are other questions. Absolutely. Sorry?
How's the value of the initiator matrix theta get?
So how that value of the initiator matrix was found? Okay, that's a very good question. I will point you basically to the paper. I will put it there. It takes a bit of time, but at the end of the day, basically, you can analyze your real network, and then you're gonna be doing some grid search basically until you get close to the values that you want. Question? It's a new opinion network. It's a social network. So it's a real network. Okay, question? Sorry, I have to speak up because there's a lot of background noise. I can't hear you. Like with different values, we will be getting... yes, absolutely. But you will not be matching all these properties, okay? It's relatively easier to approximate the degree distributions, but then it becomes harder to match the spectral analysis. So your eigenvalues will be different. Thank you. Hi.
General question.
Let me...